Okay guys, so what I'm going to do is take you through the Edexcel A-Level Maths A2 paper, which was paper 2 from 2018. For students at Morpeth School who have done this, we did this for the mock exam. Not all of the questions that I'm going to do here will actually be ones that you did, because there's a few extra ones, but I thought I'd do all of them for you so that you can look back on this for part of your revision. Okay, so let's get started. Question 1, it tells you a function of g, and it says that 2x plus 5 over x minus 3, and it says that the domain is that x is greater than or equal to 5. First thing it wants us to do is to find g of 5. So for question 1a, what we're going to do there is we're going to start off by finding out what g of 5 is, and then we're going to find out by putting that back in. So if we do g of 5, that means we're going to replace x with 5. So we have 2 times 5 plus 5 divided by 5 minus 3. So that becomes 15 over 2, or maybe that's going to be easier to use it as 7.5. So if we're trying to do g of 5, that's actually doing g of 7.5. So we're going to do 2 times 7.5 instead of x plus 5 divided by, instead of x, we're going to have 7.5 minus 3. When you put this into your calculator, you get 20 over 7.5, take away 3 is 4.5, so you should come up with 40 over 9. You get a method mark for doing this first bit and then a mark for doing this second bit that we've got here. This is where sometimes, this is where a few people started now falling down and weren't really sure what you were talking about with the range. So we've already been told the function. We've been told that the domain is that x is greater than or equal to 5. And we're trying to find out what the range is equal to. So the range is to do with the y-axis, okay? We're trying to think about what values can you possibly get on the y-axis. Many of you have got a graphics calculator, which will help you to see what's going on here. So what I've done is I've put the graph y equals 2x plus 5 over x minus 3 onto Desmos so we can see what it's looking like. But the thing we're interested in is that x is greater than or equal to 5. So if I just include that area here, the only bit of the graph that we're actually looking at is this part of the graph here. Everything in this white section will not be included. So we're actually trying to say, what are the possible values of y that you can get? Well, it looks like we get one of the values here when x is equal to 5, and then it looks like as it keeps going, it sort of trails off and gets to a particular value. So we're going to investigate what happens in these two bits. Right, our graph, we said, looked a bit like this, and we're going to try and find out what happens when x is equal to 5. Well, when x is equal to 5, we've already worked that out earlier on. When x is equal to 5, the function was 7.5, or 15 over 2. So that looks like, on our axis, our 7.5, that looks like the maximum thing that the function can be. That the maximum thing that the function can be, it's got to be less than or equal to 7.5, or 15 over 2. But we saw that it started to trail off, okay? We're going to see that it started to trail off. So maybe what we could do in here is we could substitute in a large value of x. If we say substituted in, I don't know, maybe a value of x as 1,000. If we substituted in 1,000, just to see what happens when it behaves when x gets very big, we would have 2005 over 997. And you can see this is going to be roughly 2,000 divided by 1,000. It's going to be roughly 2, but it's actually going to be a bit bigger than 2. It's going to be 2 point, let me just grab my calculator. So we got 2005 divided by 997. It's actually 2.011, like this. Now, no matter how big you make this value of the x bit, the numerator is always going to be slightly bigger than the denominator, which means it's always going to be slightly bigger than 2. So the function has always got to be bigger than 2. A different way you could think about that is we say that the function of x is 2x plus 5 over x minus 3. If you imagine x getting really, really, really big here, these bits aren't going to matter very much. So it's roughly going to be equal to 2x divided by x, which is going to be roughly equal to 2 when it becomes very big. That's how we come up with this bottom part of it that we've got here. Okay, part C of the question is asking for us to do two things. It wants us to find the inverse of the function. It also wants us to write down the domain. Many of you forgot how to find the inverse, or you confused this with doing the derivative of the function. So let's just remind ourselves, our function is 2x plus 5 over x minus 3. The way we should do this is we write it out as y equals 2x plus 5 over x minus 3. And the way I've taught you to do this is to swap the x and y values and then rearrange to make y the subject. So we'll do that swapping. We get x equals 2y plus 5 over y minus 3. And then I'm going to multiply that by the y minus 3. I'm going to expand. And then I'm going to collect the y terms together. So I have xy minus 2y equals 3x plus 5. I'm going to factorize, so I have y outside the front. And then I'm going to divide by x minus 2. So I get 3x minus 5 over x minus 2. So that tells me that my inverse function is 3x plus 5 over x minus 2. Now the question, if you remember, it asked us what is its domain. Now if you don't know this, the range of the function will be the same as the domain of the inverse function and vice versa. They kind of match up in that way. So its domain, the range was this. So the domain will be that x can be between 2 and less than or equal to 7.5. Some of you may have done this, it's 15 over 2. Either of those things is right, okay? So just as a reminder there, for the inverse function, the domain is the range of the original function and vice versa as well. Okay, question 2. This was a nice vectors question that we've got. Relative to a fixed origin, we've got this position vector here for A. Immediately, I would want to jot down this. I've got 2, 3, minus 4. I've been told out what the position vector of B is. B is 4, minus 2, 3, just getting things prepared. C has a position vector, A, 5, minus 2. It also tells us that A is less than 0. D is the point such that AB is equal to BD. Find the position vector of D. Well, they've told me that AB is equal to BD. And we know that AB is B minus A. And BD is D minus B. I know this, I know this, I know this. I want to find this. If I rearrange it to find out what D is equal to, I can add that B onto the other side and I get 2B minus A is equal to D. So I'm actually just going to calculate that. I'm just going to do 2 lots of B, which is 4 minus 2, 3. And I'm going to take away A, which is 2, 3, minus 4. Let's just keep working on this and see what we get. We then get that D is equal to, sorry, that's just the bell going. 2 times 4 is 8, minus 2. 2 times minus 2 is minus 4, minus 3. 2 times 3 is 6, minus 4 becomes plus 4. So we get that the position vector of D is 8 minus 2, minus 4 minus 3, and 6 plus 4. Okay, so this is our position vector of D that we have here. There are other ways of doing this. You could, of course, work out what B minus A is first of all, and then add B onto that. There are many different ways of doing this. This is probably the way that I would go about it. 2b, it then tells us that the modulus of the vector AC is 4. So I better work out what the vector AC is, first of all. AC, we know, is C minus A. And we've written at the top of our page that C is A5 minus 2. So A5 minus 2. And we're going to subtract what the vector A is. The vector A is 2, 3, minus 4. So I get A minus 2, 5 minus 3 is 2, minus 2 minus 4, people made mistakes here, is 2. And I'm now going to find out what the modulus of this is, and I'm going to make it equal to 4. If I want to find the magnitude of this, that is going to be the square root of A minus 2 squared plus 2 squared plus 2 squared. That would be equal to 4. Some people weren't sure how to get rid of this square root symbol. The best way to get rid of this square root symbol is to square both sides. So I've got A minus 2 squared plus 4 is equal to this part squared, which is 16. Quickest way of solving this doesn't even require this to be expanded. So I get a minus 2 squared is equal to 16, take away 4, which is 8. I'm then going to square root both sides. When you take the square root of 8, you get plus or minus 2 root 2. Add the 2 to the other side, and you get a is equal to 2 plus or minus 2 root 2. However, don't forget what the question told us. A is less than 0, so that must mean that, because a is less than 0, a must be equal to 2 minus 2 root 2. You can check to see on your calculator that gives you a negative value. Some people wrote that as a decimal. I do think it's better to leave it in that exact form that we've got there. Question 3, this is a proof question, not very well answered because I think people didn't know what irrational numbers were. It said if m and n are irrational numbers, where m is not equal to n, then mn is also irrational. It says to disprove this statement by means of a counterexample. This means find something that tells you that it's not going to be true. So we need to find two numbers which are irrational, that when we multiply them, we get a rational number. Because the thing that we are trying to disprove is that when you have two irrational numbers, you then multiply them and you get another irrational number. Why don't we show that you can actually get a rational number? So I'll give you a few examples of some things that are irrational, okay? Here are some irrational numbers. The square root of 2, the square root of 3, minus the square root of 7, pi, 1 over pi, e. Any of these things are irrational. Here are some examples of some rational numbers. 3, minus 5, 1.274, 3 over 9, minus 2.7. Rational numbers can be written as a fraction. Irrational numbers cannot be written as a fraction where the numerator and denominator are integers. Okay, so there's our bit of background knowledge for that bit. We're now actually going to find two numbers here. So I'm going to let m equal, I don't know, why don't I let it equal the square root of 2? Maybe n could be the square root, 2 root 2. Here, clearly, root 2 and 2 root 2 are not equal to each other, so we've kept that bit true. mn is equal to root 2 times 2 root 2. Well, 2 times root 2 is just 2 times 2, which is 4. mn is equal to 4, which is rational. Lots of people are able to get to this stage, but because it's a proof question, you need to have some kind of conclusion. So we need to say something. The statement is disproven because these values for m and n multiply to give a rational number. You don't have to explain it exactly in that way that I've said it, but there needs to be some kind of conclusion statement. You can't just leave it at this part that we've got here, okay? The second part of the question is sort of a proof question. It's just a little bit more in disguise. It says, sketch the graph. So let's do that in this section of the board that we've got here. It says for BI, sketch the graph of y equals the modulus of x plus 3. Well, I think you all know how to draw y equals modulus of x. Y equals modulus of x just looks like this. If I'm going to draw the y equals modulus of x plus 3 graph, well, you're just adding 3 onto all of those values. So it's going to be the same graph, but it's just going to have moved up 3 spaces. Too many people were shifting it left and right by 3. It's just going to move up 3 spaces that we've got here. The second part of the question is definitely harder. Some people did all right with trying to explain this with words. But what it says for the second part of the question is it says, explain why x plus 3, modulus of x plus 3, sorry, is greater than or equal to the modulus of x plus 3 for all real values of x. Now, the first part of the question is going to really help you to do this, okay? We have just drawn the graph, which was y equals the modulus of x plus 3, okay? Why don't we try drawing this graph here? Y equals the modulus of x plus 3. Well, this is going to be like the modulus of x graph, but because the plus 3 is inside the function, it means it's going to shift it, and it's going to shift it 3 spaces to the left. So instead of it being here like this, it's going to shift here like this, and we get something that looks like this. So this red graph is here, and the blue graph is referring to this part that we have. All this really now requires to get the second mark is we can say, by looking at the sketch, the graph for modulus of x plus 3 is equal to the modulus of x plus 3 when x is greater than 0. We can also see that the graph for the modulus of x plus 3 is above the graph for the modulus of x plus 3 when x is less than 0. You can see that here, that the red line is underneath the blue line. So we can say that the modulus of x plus 3 is greater than the modulus of x plus 3. Putting these bits together, this means for all values, the modulus of x plus 3 is either greater than or equal to the modulus of x plus 3. Because you can see here it's equal to it when x is greater than 0, and it is greater than it when it is less than 0. There are other ways of trying to explain that, but the graph is definitely the best way of us having a look at this one. Okay, so we'll have now a look at question 4. This is one that didn't come up in the mock exam, but this is going to be useful for you to have a look at from your revision, okay? So for question 4i, it says, show that the sum from r equals 1 to 16 of 3 plus 5r plus 2 to the power of r is equal to 131,798. So we can see this as split up into 3 different sequences. It's going to be the sum from r equals 1 to 16 of 3, plus the sum from r equals 1 to 16 of 5r, plus the sum from r equals 1 to 16 of 2 to the power of r. Very briefly, we'll just think about what these sequences look like. This is just going to be a 3 plus 3 plus 3, and it's just going all the way up to 16. This one is a sequence that starts with r equals 1, so it's going to be 5 plus 10 plus 15, and it's going to be done 16 times. This sequence starts with a 2, because it's 2 to the power of 1, then it's going to be 2 to the power of 2, 2 to the power of 3, 2 to the power of 4, and that's going to keep going all the way up to 2 to the power of 16. So we're just going to be adding up these 3 sequences together. This one, there are 16 lots of 3, so it's just 16 times 3. This one is going to use the formula for the sum of an arithmetic series. A reminder of that sum is it is n over 2 brackets 2a plus n minus 1d. For our particular sum that we've got here, the number of terms in the series is going to be 16. The first term in the series is clearly going to be 5, and the common difference as it goes up each time is also 5 that we've got there. So putting that in for our formula, we then get plus, okay, we're going to do 16 over 2, 2 times a, plus n minus 1, which is 15, times 5. And then we're going to have a look at this last bit. This last bit here is going to be the sum of a series that is a geometric series. So for a geometric series, what we want to think about here is we want to think about how you do the formula for that. The formula for this is going to be a brackets a to the power of r a to the power of n minus 1 over, oh gosh, just reminding myself what the formula is. A to the power of n minus 1 over r minus 1. Yeah, that's what it is. And you can check that out in the formula book as well. It's a brackets. In fact, I'm just going to grab the formula book, check that that is the right one. I think it's on page... Silly me, drawn it out wrong. The formula is a brackets 1 minus r to the n over 1 minus r. So if we now come back and actually do this last part, we can see that a, the first term in the series, is 2, n is 16, and the common ratio is also 2. So putting this all together, we get 2 brackets 1 minus 2 to the power of 16 over 1 minus 2. Then working these three things out separately, we get 48 plus, let's put this bit on the calculator and see what it comes out as. We should have, what's that, 8 times 10 plus 15 times 5 plus 680. And then this last bit here, we've got when we add these three bits together, we're hoping very much it gives us what we were asking for. So that's 48 plus 680 plus 131070, and we get 131798 as required. Okay, so quite a lot going on in that question. For part 2 of the question, we are going to try and find out something a little bit different. It's a different question because it says it's a part 2. And we've been told for part 2 of the question that a sequence is being defined as, for U1, U2, U3, it says that UN plus 1 is equal to 1 over UN. And the first one in the sequence is 2 over 3. And it wants us to find out the sum of the series from r equals 1 to 100 of UR. Okay, well, if U1 is equal to 2 over 3, let's work out what U2 is. U2 is 1 over U1. So it's 1 divided by 2 over 3, which is 3 over 2. U3 will be 1 divided by 3 over 2, which is 2 over 3. U4 will be 1 divided by 2 over 3, which is 3 over 2. So you can actually see what's happening here. We're going to be doing U1 plus U2 plus U3 plus U4, and we're going to do that all the way up until we get to the 100th one, and we know that the 100th one will be a 3 over 2. So the sum from r equals 1 to 100 of UR, well, there's going to be 50 lots of the 2/3, and there's going to be 50 lots of the 3 over 2. So what's that? We've got, when you add that together, we should get 325 over 3. Let me just double check that that's the right answer there. Yep, 325 over 3. Okay, so that's the first 4 questions. I'm going to pause this here and then we'll keep going in a moment.